Hello everybody, today we're going to talk about the 4 fundamental forces. And now firstly, we need to know this thing, like some sort of table. Well, firstly there's some quarks, up quark, down quark, and I think it's a charm quark, strange quark, and then top quark, bottom quark. These are the quarks, and underneath it there's some electrons, muons, and tau. And also there's a electron neutrino, and also a muon neutrino, and a tau neutrino. I think this table of stuff are just elemental things that make up the world. And then on the right hand side there are a thing called gluon and a thing called photon. You'll know what a photon is, the thing that makes up light. And then there's these two. Now there's this some sort of table thingy about the little particle thingies that make up the universe, and these 6 are the quarks: up quark, down quark, charm quark, strange quark, and top quark and bottom quark. And over here there's, well, these things are quarks, and these 6 are called leptons, and they're electron neutrino, muon neutrino, and tau neutrino. And this G is the gluon, and the thing under it is the photon. These 2 are Z bosons and W bosons, and this is a Higgs boson. Now we're going to talk about the fundamental forces that these things make up. The 4 fundamental forces are gravity, the electromagnetic force, and the strong nuclear force, and the weak nuclear force. Firstly, we have gravity, which is explainable by the general relativity. Now, to think about general relativity or gravity, firstly there isn't a particle for gravity. And now, firstly we have to think about a accelerating rocket or accelerating box. Here's a box that is accelerating upwards at 9.8 meters per second squared, because it's accelerating, which is the same rate of acceleration as something dropped on Earth. So if I drop this pen, this pen is accelerating at 9.8 meters per second squared. Now let's say a person is riding in the accelerating box. Then this person, because this box is accelerating, it's getting faster and faster. So because of inertia, the person feels a force pulling him downwards. Basically, we have this ping pong ball over here. We have this table thingy, and now I'm gonna put this over here. And if I accelerate this table to the left, the ball is gonna feel a force to the right, like that. Simple stuff. So the person feels a force downwards. And also, if he dropped an apple in the accelerating box, because the box is accelerating at this rate, the apple is gonna fall with the same rate. The apple is going to fall at 9.8 meters per second squared. And now, let's say there's a box on Earth. It's the same box. The person can't see the outside. The person is riding in the box too. And the person is feeling a force dragging down on him at this much. And he drops an apple. The apple falls at 9.8 meters per second squared also, as like how it was inside the accelerating box. The person can't feel anything different if he compare these two scenarios, because he can't see the outside. Well, he might be able to figure out that this one is on Earth because there's gonna be a little bit of difference in the force, something that he feels as a force pulling him downwards of the higher part and the bottom part. There's gonna be a minuscule difference between the two, but anyways, these two are basically the same. So the box on Earth has the same physics as the accelerating box. So now let's poke a hole through the box and shoot a laser. Because the box is accelerating, the light is gonna curve a little bit. Well, because the box is accelerating, light goes straight and it accelerates. If this is the light and the box is accelerating, the light is gonna look a bit curved because the light is going straight, and well, for the person, and that's just gonna be how it looks. So that means if we shot a laser over here, because the physics work the same in these two boxes, the light is also gonna curve over here as well. And you can see that this is Earth, and now Earth can use gravity to curve light, and this happens because, well, the physics works the same, so this should work. The gravity, the mass of Earth, basically curved the space-time around the Earth. So a straight line in this space-time is a little bit curved. For the light is just moving in a straight line. The light is just moving the shortest distance it can travel from over this spot to move to that spot. Because the space-time is curved over in this area, the fastest way to get from here to there isn't this, but it's more like that because it is curved. And also the curvature of space-time makes this fall like it was accelerating. And that is gravity, or general relativity. The next one, the electromagnetic force. The electromagnetic force is caused by the photon, or that force is delivered by the photon. What electromagnetic force is it's the force between different charges, force acting between two protons, let's say. There's a proton here, and there's another proton here. And now the protons, they both have one positive charge each, and they have the same charge, positive, so they push each other. Because it pushes each other away, well, that's the electromagnetic force applying over here. And so now would zoom off if you put these two like that. And well, that's also the same for electrons. If you put two electrons side by side, it will push each other away too. But if there's one electron and one proton, well, these two are gonna pull on each other, because now they have different charges, and the electromagnetic force makes them pull on each other. And the electromagnetic force is 10 to the power of 36. 10 to the power of 36 times more powerful than gravity. We can think of this one as when you rub a balloon on your head and stick it onto a wall. When you rub a balloon on your hair, the electrons get exchanged between two, and then the balloon ends up with more electrons. And now if you put it onto a wall, some electrons on the wall are pushed away from the balloon because of the extra electrons on the balloon. This is the wall, this is the balloon. There's some extra electrons, and so the electrons on the wall are pushed more into the wall, kinda. That means the part of the wall that is more closer to the balloon is a little bit positively charged, which produces a pull between the wall and the balloon. So the balloon sticks onto the wall. But if you measure it, the exchange of electrons that happen between your hair and the balloon is very minuscule. Well, I mean that electrons move only a very, very little bit from the hair to the balloon, but it still manages to stick onto the wall. That is because electromagnetic force is so much stronger than gravity. Earth's gravity is pulling it down. Even though Earth is a very massive object, the electromagnetic force acting between a very, very little amount of electrons, these are so strong that they can stick onto the wall even though gravity is pulling them down. This shows how much gravity is weaker. Yeah, I think that's about all about electromagnetic forces. And now there's the strong nuclear force. The strong nuclear force is transmitted by a particle called gluon. The strong nuclear force is, let's say here's a particle and here's another particle. For the strong force to apply on these two, the distance between has to be less than 1 femtometers, which is 1,000th of a nanometer, which is a very, very, very small amount of space. But the strong force is the most strongest force in the universe. But because the distance that the strong force can apply is so short that the strong force isn't the force dominating the universe. But the electromagnetic force, which was 10 to the power of 36 times more powerful than gravity, also doesn't dominate the universe. Gravity does, the weakest force of the four. The reason for that one is because for the electromagnetic force to work, things need to have different charges. But the bigger the stuff are, the more neutralized the charges are. Well, if you think about it, that just makes sense because it's so big that the things are becoming more neutralized, exchanging more electrons with each other. And if you look at the grand scheme of things like the mass and stuff, it's very huge. It is basically neutral, so the electromagnetic force can't pull the things together or push it apart and stuff. But gravity applies better if the things are bigger. So that's why gravity is the dominating force. And strong force applies on quarks. So if you look at a proton, there are 3 quarks inside, 2 up quarks and 1 down quark. Also, one interesting fact, a up quark has a charge of positive 2/3, and a down quark has a charge of negative 1/3. So if a proton is made out of 2 up quarks and 1 down quark, and then the proton would have 1 positive charge because 1 of these and 2 of these combined equals 1. And now there are quarks inside the proton, and these quarks are pushed into each other in a very tight space, and the distance between is less than 1 femtometer. So the strong force applies. So basically there's a little connection there made up by gluon, and this force is so strong that it holds quarks together and makes the proton able to exist. And the same for the neutrons. And also, here's a neutron. This is a nucleus of a heavy hydrogen, which has 1 proton and 1 neutron in it. And the distance between these 2 particles are small enough for the strong force to apply. So the strong force applies, and it pushes these 2 particles together. And that's how nucleuses of nuclei of atoms and stuff can be stuck together. It's also for protons and protons, or neutrons and neutrons. That's how nucleuses just stay together and not get exploded and stuff. And now finally there's the weak nuclear force, which is about 10,000 times weaker than the strong force. And the weak force, what it does is it makes beta decay happen. And what beta decay is, basically we have a neutron here, and now the neutron can be are split into 3 things, which are a proton, an electron, and an electron neutrino. That's basically what beta decay is. I think what also the weak nuclear force does is that if you put a proton and an electron together, I think it gets formed into 1 neutron, and I think that's how that's the doing of the weak nuclear force. That's about all that I wanted to explain in this video. And to summarize, there's gravity, which happens because mass curves space-time, and there's electromagnetic force, which is caused by the photon and is very, very strong compared to gravity. And there's the strong nuclear force, which puts stuff together. And there's the weak nuclear force, which does these stuff. And okay, bye.